So now we are going to do model building, right? We're going to find out steps in model building. We have discussed what simulation is and what is a model. A model is basically a representation of a system, and simulation is basically the change in the variables that affect the model to see different outcomes, right? Considering this in mind, we can how can we build a model, right? How can we build this interface to work with, in which we would be doing some animations? How can we work this, right? How can we make this? There are several steps to it, and the first one is problem definition. And the problem definition is defining the problem you have. You are going to define it, right? Yeah, so we were talking about the first step for building a model. And the first step is to define the problem you have, right? You're going to define the problem, like for example, what aspect of the system that you want to solve for and you want to model for. So there may be the case that we aren't going to model each and every aspect of a system. Maybe we take some aspects that are really, really related with the problem, and then we model those aspects. Then we have a scope, and this leads us to the scope point, which literally means that the model can scope to which specific details. Like we have different things going on in a system, and which are the aspects that we need to really work with, and which are the aspects that we can just ignore, right? So the first step, we defined our problem. We talked about the aspects, defining scope, and which aspects to be included in the system. Then we have system conceptualization, right? And what this does is it conceptualize our system. So we have defined the problem now, and now we are going to define the problem in terms of the concepts. We're going to start with what are the system boundaries, what are the state variables we talked about, and what are inputs and outputs, what is a feedback loop, right? So feedback loop we haven't talked much about, but it's basically when your system is designed to give you some feedback. You would have a negative feedback or you would have a positive feedback, and based on these feedbacks you are going to take measures in your simulated system, right? So this was the intended purpose, and you have defined your problem into these four categories where you are asking for system boundaries, the state variables, the inputs, outputs, and the feedback loop. Define the problem and then conceptualize the problem into these four categories, right? And now it says that this step involves simplifying these systems further and further and further, so we can work with all the other incoming steps more easily, right? And we should avoid overcomplication and oversimplification of the model. The third step is the choice of modeling approach, right? I have defined my problem, I have conceptualized it. Now I need to understand what is the modeling approach I should use to really make the model for the problem I'm choosing, right? Maybe you're gonna go with something on mathematical models, where would you use the equations, the mathematical equations, and they have given example like the motion of a pendulum can be modeled using Newton's law of motion, right? So when we were little, or when we were in our high school, we studied that we have a pendulum, and it has this movement, right? And it has some downward force like weight to it, and some upward force, that's tension here, and there was other forces existing towards it. So this was, there was some idea of Newton's law here, like F equals to ma, mass acceleration things. Um, and it shows that the actual problem was actually the measure of a pendulum, right? But the physicists describe it in terms of mathematical models using Newton's law of motions. Means you define the problem, you conceptualize the problem, and then you divide the concepts into the mathematical or whatever the models you're using representations. All of them will be at some sort be converted into mathematical representations. Then we have statistical models like for the randomness or stochastic or the models which involve like randomness, or they are mostly dealt with probability things. And for example, weather patterns can be modeled using probabilistic models, right? Then we have discrete event models where change occur as specific events, and queuing systems can be best represented using discrete event models. We have agent-based models, which means that when you need to simulate the behavior of individual entities or agents, right, that interact with each other, such as in social or economic simulations, right? For example, I want to build a system for a finance department of my, country, right? A big thing to do, isn't it? So I want to track down these economic conditions and the finance conditions there. So I can just automate or simulate every aspect of finance, like how the assets are basically related to bank, yeah, right. And how the bank is basically related to the investments, and how that's going to give money to the government. Like these are all little parts of simulation that you can simulate individually, and then they can interact each other to form a big picture of the simulation. So these were agent-based models, and this is used in social or economic simulations, like bigger picture you want to see. Right, so this was our third step where we formulated the model. The fourth step is where we chose the model. The fourth step is to formulating the model. Means we chose the model, we made it as a conceptual, but now we want to choose it as a formal model that can be stimulated, right? So if the system is continuous, then a model will um, also be affected. Means we are going to basically convert our model to representations of the models that they choose. For example, I chose the model of mathematical, so I need to convert my problem into or represent my problem into equations, right? This is what I need to do for formulating the model. So say if the system is continuous, like it's changing at regular intervals, then I would need to use equations to see how the state variables are changing. If the system is discrete, like the social networks or digital circuits, then I would use the state transition diagrams or logic rules or discrete event algorithms to specify and formulate the model, right? And the important thing to note here is that state transition diagrams are like this. For example, when something is empty, like for example for a queue, when a customer came in, or when a customer got back. So this is the state transition diagram where we use a state and then we use arrows to represent the specific action that either someone is coming in or going out. Okay. So this was our discrete system. And this was our fourth step where we formulated the model. And it says if we often use mathematical or computational tools to describe the relationships and the dependencies, right? The fifth is the parameter identification. Once you formulate your model, you need to identify and quantify the parameters of the system because they are going to help you build the state and control the state of your system. They can be physical constants, rate coefficients, probabilities, and boundary conditions. Most of the time, they're going to be probabilities. If you're really you're working with random models, we are going to mostly likely see probabilities. Of course, these are really associated with those scientific models as physics or chemistry. These parameters are often determined using experimental data or literature values, yet a model's accuracy heavily depends on the correct estimation of these parameters. So really, really important stuff. And how do we generate the values of these parameters at specific interval, right? The sixth point is also really important, and a lot of times it's asked a lot. So what is the difference between calibration and validation? So after you formulated the parameters, how would you know that the model is working fine? What is calibration? The model is tested with the known data to ensure that it behaves as expected. During calibration, parameters might be fine-tuned to make the model better match real-world observations. Validation. After calibration, the model is validated by comparing its outputs against independent data or known behaviors of the real system. This step ensures that the model is an accurate representation of reality. So we need to understand this in a little more detail. So in the model calibration, we already have the data, right? Known data, right? So when we are always making model, like we need to have some kind of data to test the model and some kind of data to validate the model, right? I think the same thing, but in the calibration we have the known data that we that we test our model so that we can say that our model is working fine with our own data, the data we knew already, and the parameters maybe change a little so that they can better match the real world and test it better. After calibration, as we have tested with our own data, we validate it with independent data, the data it doesn't know, or the real systems. For example, as we talking about this, we often talk about the LLMs like the ChatGPT, how it uses data to train, how they use data to train it. So in this case, they test the functionality by first giving the data they have, and then they check the functionality by getting the data from the real systems like these, right? Maybe the Claude or the Gemini, they would take the ChatGPT's behaviors and they would test those behaviors on their own LLMs to validate them, right? Because we need to really, so calibration is mostly like when you are in your house and you are being tested by your parents, and validation is when you are gone, you're outside the house and you're tested by your teachers and you need to perform even better, right? So a good analogy to learn the stuff better, right? So this point is also really important. Then so we got a simulation. So once the model is built, calibrated, and validated, it is used for simulation. This involves running the model under various conditions to explore how the system behaves in response to changes in inputs, parameters, or other variables. Now, there's a difference between inputs and parameters. Inputs can be, any input you're giving it to your system. This depends on the system, okay? So if I'm talking about the finance, the input could be the assets or the data from the bank or the investment data, but the parameters are the specific data that we basically fix ourselves so that our systems can work accordingly to the parameters, right? Or other variables, simulation is out to explore what if this happens scenarios, helping predict outcomes under different circumstances. So we get this simulation. Next, we do analysis and interpretation. The results of the simulation are then analyzed to answer initial questions, and interpretation involves understanding how well the model captures and assesses the results' reliability. So analysis means that we check that, how much the model is performing well, that is it solving the problem it was supposed to solve, and interpretation means to understand that how well the model is performing in reality. Then we have refinement and iteration. It is often an iterative process. After initial simulation, you might need to refine the model, and you may improve the parameter accuracy, or you may, adjust the assumptions. And this cycle is going to be continue until the model is accurately going to represent the system it was intended for, right? So these were our 9 points in model building. First, we define the problem. Then we conceptualized the problem. Then we chose a model. We formulated a model. We identified the parameters. We calibrated and validated it. Then we did simulation, analysis, interpretation, refinement, and iteration. Let us revise it once more. So first of all, what we did, we defined the problem, we conceptualized the problem, then we chose the model, we formulated the model, we identified the parameter, we have calibrated and validated it, then we simulated it, we analyzed and interpreted, and refinement and iteration. So these are 9 steps that are really important, and it could be asked to you. In the next video, we're going to talk about type of models, and they are going to be quite similar to the type of systems we have studied, but it's more important to understand the difference between models and system. So yeah.